Hello everyone and welcome to the fourth and final lecture on kinematics. In this video lecture I will explain to you the use of polar coordinates as a special application of using other coordinates. Sometimes we encounter problems of which the motion is easier to express in terms of polar coordinates than in terms of Cartesian coordinates. So how to do this transition is important to know. To explain this, let's consider a point mass located over here that is free to move in the two-dimensional space. Now let me also draw the Cartesian coordinate frame xy, which is a fixed coordinate frame, and let's do the analysis. So we have one point mass, and as a consequence we have two generalized coordinates, namely x and y, the location of this point mass. Now, if this point mass is free to move, there are zero kinematic constraints, and hence the degrees of freedom are 2, x and y. Now, let's say we want to use polar coordinates instead. So rather than x and y, we will use r, the radial distance from the point mass to the origin, let's call that O, of the inertial frame, of the fixed frame, and the angle theta in between the x-axis and r. Now, if we are to introduce these additional coordinates, this would mean that the total set of generalized coordinates q of this problem now consists of our original coordinates x and y, but now also of r and theta. Okay, as explained in the previous lecture, we can introduce these coordinates, but of course the number of degrees of freedom still is 2. So we can only do this if we make sure that in this formulation the number of constraint equations is equal to 2. Now, of course, these are not physical constraints, but these must be two relations that express our old coordinates, x and y, in terms of the new coordinates, r and theta. So in this formulation, we will use as independent coordinates r and theta, and as dependent coordinates, we will use x and y. And the question is, how do we express the dependent coordinates as a function of the independent coordinates? So that is our first challenge. Now, these two relations can be obtained from the figure that I draw, in the sense that x can be expressed as r times the cosine of theta, and y can be expressed as r times the sine of theta. Okay, so these are in fact these relations between x and y and r and theta. Now, for the remainder of the analysis, I'm also interested in velocity and accelerations and the relations between the dependent velocities and accelerations and independent velocities and accelerations. And because both r and theta may change in time, this is going to be quite tedious. And in order to save me some writing, I will make an abbreviation as follows. I will write the cosine of theta simply as c and the sine of theta simply as s. So it's a bit cheating, but I introduce c as the cosine of theta and s I will define it as the sine of theta. It saves me a lot of work. Because here we go with the differentiation. Let's have a look at the expression for x dot. So we need to consider that r may change in time times the cosine. And this cosine also changes in time because theta changes in time. So this will then be minus r times theta dot times the sine. So you see already two terms appearing on the velocity level. Now let's go to y dot. So r changes in time times the sine. And then the derivative of the sine is a cosine. So we also have r times theta dot times the cosine. Okay, so indeed here recognize that the dependent velocities are a function of the independent velocities, r dot and theta dot, but also still of the independent coordinate theta, which is inside the cosines and sines. Okay, let's differentiate once more. X double dot. So we have the derivative of r dot, which is r double dot, times the cosine. Then we have the derivative of the cosine, which is minus sine, times theta dot. So we have minus r dot theta dot times the sine. And then we are going to differentiate the second term, which will produce three new terms. So first we have the derivative of r times theta dot times sine. So that is r dot theta dot sine. That's exactly the term I already have here, so I just put a 2 in front. And then we have minus r times theta double dot times the sine. And then we have a minus r theta dot squared times the cosine. Be careful that there's an extra theta dot produced from the chain rule. So you see 4 terms appearing. Now this will also be the case for the expression for y double dot. So we have r double dot times the sine. Then we have the derivative of the sine is the cosine times theta dot. So this will be plus r dot theta dot times the cosine. And then we move on to the second term, and then if we differentiate the r, we get r dot theta dot cosine, which is exactly what we already have. I put a 2 in front. And then we have plus r theta double dot times the cosine. And then finally the derivative of the cosine is minus r theta dot squared times the sine. So we see 4 terms. And indeed, maybe it's good to write that down, that we have that the dependent velocities are a function of independent coordinates and independent velocities, and that the dependent accelerations are a function of the independent coordinates, the independent velocities, and the independent accelerations. Okay, nice example where we see that we have all these dependencies. Okay, then in this expression for the acceleration, we see 4 terms appearing. And 2 we can recognize from the previous lecture. Maybe start at the back. We have r times theta dot squared. This is the centripetal acceleration. Centripetal acceleration. And this term over here, r times theta double dot, that we can recognize as the Eulerian acceleration. But now we have 2 additional terms that appear due to the fact that r is not constant. Over here we have a term r double dot. This is called the radial acceleration. It's the acceleration outward. And then finally the term 2r dot theta dot, that is called the Coriolis acceleration. Okay, so 4 terms makes it kind of complicated. I think it's a very good idea to make a kinematic diagram where we include, maybe here in blue, the r, the x and the y frame, like this. And let me now switch to green as I draw these accelerations. So the radial acceleration is positive in x and positive in y direction. It's radially outward like this, r double dot. Then the Coriolis acceleration, you can see that it's negative in x and positive in y direction. So that means that it is in this direction. Okay, so this is 2r dot theta dot. Now the Eulerian acceleration is in the same direction actually, because you see that it's also negative in x, positive in y, has a sine component in x and a cosine component in y. So also this Eulerian acceleration is in this direction, r theta double dot. And then the centripetal acceleration, negative in x, negative in y. So that must be in this direction. Indeed, again, like the previous example, in the direction of the point about which we are rotating. Okay, so this is the kinematic diagram for this case. Kinematic diagram. And yeah, you can see that in this case, the use of polar coordinates comes with 4 different types of accelerations. That makes it useful to visualize this in the kinematic diagram. All right, this concludes the lectures on kinematics. Thank you very much for watching.